You're now listening to The Brian Callen Show with your host, Brian Callen.
Okay, guys, our sponsor is DraftKings.com. And DraftKings.com is, I'm not a big fan of gambling, but this is not gambling. This is intelligent. I guess it's intelligent gambling in terms of you're not going to win unless you really understand your team and you understand this game. And that's why I think it's awesome. Football season's just around the corner, and you can get your piece of $5 million during kickoff week at DraftKings.com. It's a 1 week fantasy football site. You've already been scouting players for your season-long team. Use that knowledge to win instant cash at DraftKings.com. And apparently last year, one player turned $11 into $4,000 in one weekend. Think of all the pizza you could buy. And now you can get that operation. Another player won, ready, hold, $1 million in one day just playing fantasy football. But the cool thing is you better know your football. It does favor the person that knows the game. You've got to be skilled. It's not just by chance. Fantasy football is way more exciting at DraftKings.com when you can win huge cash starting the first week of the season, because cash is exciting. It's the American way, ladies and gentlemen. So DraftKings.com. Bigger events, bigger winnings, bigger millionaires. And guess what? If you use promo code Callen, C-A-L-L-E-N, that's my last name, you'll get free entry into the Week 1 $5 million Kickoff Bash. Enter Callen, C-A-L-L-E-N, for free entry now at DraftKings.com. DraftKings.com. Ladies and gentlemen, our guest is Professor David Goldberg, who is a professor out of the Department of Physics at Drexel University. And you want me to call you Dave, which I love.
Please
and,
do, yes.
And I will. Of course, if I had a PhD in physics and I was a professor, I would have you call me Dr. Professor.
I asked my wife to call me that, and it hasn't worked out so well so far.
What a surprise. Do you ever do that? Just, listen, go do that because I'm the smarter one. It doesn't work, does it?
No, it does not.
I understand. You are, I just love, you kind of have this little thing here where you say, I joined the astrophysics group in the physics department at Drexel in the fall of 2001, currently the Associate Dean for Research and Graduate Studies in Science for the college and Director of Undergraduate Studies. And you go through this. This is for your students. And you said, I'm also very involved in research. Most of my work centers around cosmology in some way or another. I'm interested in gravitational lensing and in particular in extracting additional information out of weak lensing signals of galaxy clusters. All right. But I just love that your first book is a user's guide to the universe, and the book we'll talk about here is The Universe in the Rearview Mirror. And one of the things that we were talking about is you make a lot of your ideas so accessible. And talk to us a little bit about the big idea here in your book, The Universe in the Rearview Mirror, which is essentially that the meaning to life and things is all about symmetry.
Well, maybe not the meaning to life, but certainly a bit about how the physical universe is put together. So we were chatting a little bit beforehand, and one of you gave me a very common story, which is, I took this physics class and it was really hard and I just didn't get it. And, this is a very common experience, and it's something that I meet people all the time. If I sit down on a plane and I start talking about what I do, they're like, oh, physics, I hated that class in high school, or I hated that class in college. And this is just such a common experience because, in large part because of how we teach it, because of what we expect people to know and do with it, which is basically, I think to most people's perceptions, to come up with some giant list of equations and you memorize them, and then somebody gives you some numbers and you plug them in and you get an answer, which is totally not what we do, and it's totally not what we should be conveying to the rest of the world. We being physicists, in this case, I'm counting you in the club.
Right. Thank you.
Yes.
Thank you. Because yeah, you're right. I think where science falls short for a lot of people is it gives you maybe equations that are true, but it's a little bit like describing a human being with their genome. I can give you a number and describe where you come from, but it doesn't really tell me why you are the way you are, or where you who you really are, right? There's a different kind, and I think that what you seem to do is is bridge that gap.
Right. And so one of the things, or I hope to anyway, one of the things that I try to do is I'm trying with especially the universe in the rearview mirror to sort of show you what it's like from our perspective, to show you what it is that when physicists walk around and saying, oh, the universe is so elegant or beautiful or whatever, we're not just trying to sweep the equations under the rug, but to sort of say, well, in fact, the reason we're so excited about this is not because there's this huge equation that we're ending up solving and isn't that nice. It's that where the equations come from something fairly simple. And the guiding principle in this book is something called symmetry, something that shows up in mathematics. It shows up certainly in all sorts of things in nature.
I'm sorry to interrupt, but I should have said that the other part of the title is how hidden symmetries shape reality.
Yes.
Yeah.
Right. And so there are non-hidden symmetries, of course. There are things you see all the time. I mean, your left and your right, for example, look more or less the same. You look at yourself in the mirror, you flip yourself in the mirror, you still look like a viable human being. Although we know in there's little asymmetries too. You know, your heart is to the left, not to the right. But for the most part, we look symmetric. There are all sorts of things with you mentioned DNA and genome. We think about the beautiful spirals of DNA and how that looks, the double helix of the DNA. There's a symmetry there as well. I mean, there's all sorts of symmetries that just show up in nature, show up in art, show up in architecture, all over the place. And we see them, and we can say, isn't that beautiful? It appeals to our mind. I mean, here's one that just shows up, again, outside of physics, but one that sort of points to how people enjoy symmetry, even if it's even in a word-oriented context. So I'm a big fan of crossword puzzles, for example. And even if you've never done a crossword puzzle, you'd recognize what the grids look like. There are white squares, there are black squares. But did you know that there is a rule when constructing American-style crossword puzzles that the black squares always need to look the same if you take the entire puzzle and you either rotate it around 180 degrees, that is to say a half turn, or you flip it like it's looking in a mirror. They need to look exactly the same. Those are symmetries. I mean, this is what symmetries are. Take something, do something to it, and it looks the same after as before. Now, it turns out that the mathematical idea of symmetry has been around for forever. I mean, just about forever. I mean, certainly since the ancient Greeks. Symmetries have been aesthetically beautiful since probably before then.
I'm thinking of the Da Vinci Code where he talks about the number phi.
Yes. So this ratio, and you're making a rectangle that's very, very pleasing, and you can do all sorts of things with it, and the ratio remains the same. Exactly right. So, and obviously there's an air, just as you mentioned, the Da Vinci Code, there's sort of an air of mystery that sort of surrounds surrounds anything numerical, because you're like, it just seems almost like magic.
Right. It's the number of the universe and all that, that explains
exactly.
Yeah.
When the real number of the universe is, of course, pi, but
right.
But it turns out, that there are these very, very basic principles of symmetry that show up and describe the universe as a whole, and really making no other assumptions than that certain symmetries exist in the universe. It turns out that you can say all sorts of marvelous things, all sorts of things that ultimately, do give rise to equations, but come from something much more fundamental. So I can give you a couple of quick examples. Some are surprising, and some are very intuitive. Let me start with a really intuitive one, which is the universe doesn't know the difference between left and right. Now, I know what I mean. The universe doesn't think anything, so there's nothing for the universe to know. But what I mean is that the laws of physics don't seem to really distinguish between the left and the right. At least not obviously.
Well, you were even talking about the fact that the same thing with the present and the past.
That's true. You've jumped ahead to one of the more non-intuitive ones.
Okay. Sorry. That's how my brain works. I'm
Brian
so smart.
But
the point is, you take your big particle accelerator and you run some sort of reaction in it, and you take that reaction and then you look at it in a mirror. the mirrored reaction looks just perfectly valid. In the same way that, when you're in a restaurant and they've got one of those big mirror walls to make the place look more spacious, you will, if you're not paying careful attention, you'll see the other room. You'll be like, oh, yeah, there's another guy in there that looks like me, whose, companion looks like my date.
Right.
You'll see that, and then that looks perfectly valid. If left and right were really, really different, you'd look into that other room and be like, ugh, what's going on in there?
Yeah, yeah.
So there's a sense left and right are basically the same. There's a very, very minor difference that turns out to be important. Maybe we'll get back to that later in our discussion, but I don't want to rush things. But then there are, as you point out, some things that are very, very surprising. So, for example, the past and the future are not distinguished in any meaningful way. So if we take a movie of some particle interaction, and two electrons scatter off of one another, or whatever. I mean, maybe something more complicated than that. And you take some movie of it, and you run that movie in reverse. The thing in reverse will look like a perfectly valid reaction that can occur. Now, and another way of saying that is the laws of physics don't care about the past versus the future, which one is which. And yet, clearly, there is a difference between the past and the future. You remember one of them, I'm assuming the past.
Sure.
You remember one of them, but not the other. Right? There is clearly some way in which this symmetry, this thing that we don't care whether it's this or that, whether that symmetry breaks. Now, we have, for that particular case, we actually have sort of a sense of why it might break. It's this fairly scary-sounding thing called the second law of thermodynamics. And we basically say, the only way in which the past is really different from the future is that over time, there's this thing called entropy. Disorder is sort of the common way of thinking about it. That disorder increases. And, which is... the standard sort of example is, you take a bunch of cue ball on a pool table, and you rack up the rest of the balls into a triangle, and you hit it. Well, the balls are going to come to rest in some fairly complicated pattern on the table. It started off in a very high degree of order. It ended up in a very high degree of disorder. But the thing is, you can't, while it is physically possible that you then hit the cue ball into the other balls and they rearrange themselves, and after finishing up scattering, then nicely rearrange themselves back into a triangle, that's very unlikely to happen. In other words, another way of saying it is there's a lot more ways for balls to be scattered all around the table than for the balls to be arranged in a nice, neat triangle.
Right.
And because the one is more likely than the other, over time, we go from high order to high disorder.
Oh, wow. Okay.
So, but that's really all we know about it.
So what does that say about time?
Well, that's the whole point. So here's the big question, and one we don't have the answer to. Like I've already said, from sort of a fundamental physics point of view, there is no difference between the past and the future. And that the only thing that really distinguishes the past from the future experientially is that things become more disordered with time. But the thing we don't know the answer to is whether the arrow of time, that is to say the direction from the past to the future, is a thing that exists, like absolutely in some fundamental sense, and then entropy increases with time, or whether, there's two possibilities: entropy can increase or entropy can decrease.
I was going to say, it sounds
and then
like
the arrow of time is determined by that.
Right.
We honestly don't know, and different people believe different things. Honestly, I'm kind of agnostic on it because it's one of these things that I don't know that we'll ever be able to get the real answer to. But there's all sorts of very, very strange symmetries that come up as well. I mean, so for example, we're made of stuff. We're made of matter, protons, neutrons, electrons. And one of the things that we found very early in the 20th century is that there should be antiparticles. An antiparticle of an electron is called a positron, for example. And it's the same sort of thing, except it has the opposite electric charge. But otherwise it's identical. It has the same mass, has the same what's called spin. they look very, very similar, but they have opposite electric charges. But the thing is, and they're not very common, but we can make them. We can make them in labs. We can make them in accelerators. They're produced in very small quantities in stars.
And you're talking about, this is antimatter, things that you can't really necessarily see?
No. You're perhaps thinking of dark matter that we can't see.
Okay.
Antimatter we can see, and not only can we see it, if I took some antiparticles and threw it at you, you would see it quite spectacularly, because one of the things that happens when you take antimatter and combine it with matter is they annihilate completely. So you take an electron, you take a positron, you bring them both close together, and boom, both of them get annihilated completely and absolutely.
They just disappear.
And produce energy. And they produce E equals mc squared's worth of energy. That's the famous Einstein equation, where c is this number, the speed of light, which is a very, very big number.
Yeah.
And so one way of saying that is a very, very small amount of mass produces a great deal of energy. So this shows up in science fiction all the time. People have these antimatter drives, and the reason that antimatter drives are useful is that you take some matter, you take some antimatter, you combine them, boom, and then your ship will go very fast.
Oh wow! Okay.
So
it's a nuclear reaction.
Yeah,
right?
but that's the thing. Is in a nuclear reaction, you destroy a tiny amount of a fraction of an atom.
Yeah.
With this, you're destroying the entire atom.
Exactly. It's far more efficient than we are ever normally able to do. So because, again, when we do a nuclear reaction, we're doing something like taking hydrogen and turning it into helium. And helium, 4 hydrogen atoms compared to a helium, it's 0.7% more massive, very, very tiny fraction. This yes, you get 100%.
What are the implications of being able to take antimatter and matter and putting them together like that? I mean, that sounds like you could make a bomb that would blow up everything, right?
You could if you had that much antimatter. Now, the thing is, there's not that much antimatter around, which is
God.
its own mystery, exactly like the Arrow of Time mystery, because we've got this big question, right? We are made of matter. The Earth is made of matter. It's a good thing, right? If you were made of matter and the Earth was made of antimatter, boom, you'd blow up and die.
Sure.
The solar system's made of matter. The galaxy is made of matter, and we see particles from the galaxy. Other galaxies are all made of matter. We'd be able to tell galaxies do collide with one another, and if there were some matter galaxies and some antimatter galaxies, when they came in contact to one another, they would, boom, blow up in a very, very spectacular way that we'd be able to see basically across the universe. So, as near as we can tell, everything that is made up of matter, with only the tiniest fraction of particles ever being antimatter, and those are just created temporarily until they get destroyed.
Well, that ratio then is not symmetrical, is it?
Exactly right. But it should be, because every experiment that we've ever done creates matter and antimatter in equal quantity, or destroys matter and antimatter in equal quantity.
Wow. So we can't really replicate how the universe works in an experiment then.
It's certainly not how the universe must have worked in the first tiny fraction of seconds, something like 10 to the minus 35 seconds after the Big Bang. Because as near as we can tell, at those energies, there's some physics that we haven't yet discovered that must have been at work that basically made matter and antimatter be different than one another. Because otherwise, if you took every particle in the universe, like in the experiments that we're able to do, if you took all of the matter and turned it into antimatter, and what little antimatter there is and turned it into matter, and filmed it and looked at the outcome, you wouldn't be able to tell that you were dealing with antimatter rather than matter. You can't tell the difference. The physics, just like the universe can't tell left from right, it can't tell antimatter from matter. Huh. We call the stuff in the universe matter because we're egocentric, right? We call the stuff that we are made of ordinary stuff. Mm-hmm. But there could be some other creatures, in principle, there could be some other creatures from another universe looking at us and be like, what are these people? They're crazy. They're calling what they're made of matter. What they're made of is clearly antimatter, and we're the ones that are made of matter.
It's just such a mind blower. Like you were talking about galaxies, and I thought to myself, how many galaxies? Do we have any idea how many galaxies might be in the universe, whatever the universe is?
I can give you sort of a rough minimum.
Yeah.
Minimum, because we don't know how big the universe is.
Right.
All we can see what's called the horizon. There's a maximum distance that we can see, and the reason is that light travels at a finite speed. In very, very fast. It takes eight minutes or so for light to reach us from the sun, for example. It takes a nanosecond, about a billionth of a second, for, say, your screen or your book, the light from that to reach your eye. But it can take millions of years for light to reach us from even the nearest galaxies, and billions
billions of years?
For the nearest galaxies, it can take anywhere from tens of thousands to millions of years for light to reach us. And for the most distant, billions with a B years for light to reach us. But the universe has only been around for a certain amount of time. It's only been around for about 13.7 billion years, and light can only travel at the speed of light. So we only see a finite distance, and the maximum distance that we can see is called the horizon.
Yeah.
But within that horizon, there is of order, about a quadrillion galaxies.
All right, hold on.
It sounds like I'm making up big numbers.
It's so nuts.
I might as well say a zillion.
I was going to say, because a quadrillion, correct me if I'm wrong, might be 250 million billion?
Well, it's a quadrillion is 1 million billion.
It's 1 million billion.
Right.
All right.
So net worth.
Yeah, I feel like we should end the interview. I should just jump out the window because there's no point.
Fortunately, it's a first-story window, so
that's true.
Yeah.
But anybody, boy, I'll tell you, it must be simply impossible when you're a man like yourself who studies this kind of vastness, these kinds of numbers. It must be impossible to be at all egocentric.
That's right. I mean, it's what's funny though. I mean,
I'm so humbled, I guess.
Well, you should be humbled,
yeah.
Right? But what's funny about it is there are. I mean, I listed some of the obvious symmetries. There's no difference between no obvious difference between the future and the past, or left and right, or matter and antimatter. But it turns out, there's all sorts of other big symmetries, and one of them, for example, is that there's no special place in the universe. And that turns out, by the way, to have huge implications. Like, it sounds like such a simple statement.
Yeah.
Like, there's no center of the universe, there's no edge of the universe. That's one of the implications. But it turns out that for many purposes, because there's no center of the universe, there's no place in the universe that's more special than any other. You may as well pretend like you're at the center of the universe.
Yeah, sure. I mean,
sure, but the calculations work out fine. That's the nice thing about it. So it's like, yeah, if you want to pretend you're at the center of the universe, you go ahead and knock yourself out.
Well, nobody else is watching.
Right.
It's just the idea that there isn't other life forms, or I don't even know honestly how to put it into context. We don't have, in many ways, the faculty as where you're walking around in your life. These things are so irrelevant in some ways, but they are obviously very relevant to another reality. And thank God people like you are trying to figure this out. But I mean, I also understand as you speak why so many scientists have a very hard time with traditional mythologies, traditional religions, because yes, Christianity and Islam and Judaism and Buddhism have their answers to our lives here in many ways, and they serve their purpose, and I have respect for them. But, when you start talking about the things you're talking about, it must be very difficult not to that is its own religion. I mean, it's such a vast subject that you'll never get to the end of.
Well, I
don't know.
We're speaking about our own personal beliefs. I happen to be an atheist. I think a lot of scientists are, but certainly not.
But I understand
all.
why. Is I guess what I'm saying. I
But it's funny. I mean, because even within the scientific community, there are definitely things that many scientists will sort of consider legitimate areas of inquiry, because there's something we can test in a lab, or even if we can't test it now, like in principle, we could go and we could build some contraption.
You can measure it.
You could, and even if you can't yet now, it's like, maybe we'll go and be able to measure this theory later. So, for example, I mentioned this whole thing about like where does the difference between matter and antimatter come in? Like, we know that matter won compared to antimatter. We know in the early universe, there must have been very close to equal amounts, and almost all of it annihilated, except a little bit of matter left over that forms the basis of us. But we don't yet really have a model for what exactly the fundamental difference between matter and antimatter is. This conservation law was broken at some point. We don't know how. We don't know why. But the idea, I mean, we have a task ahead of us, right? We're supposed to come up with, here's a theory, and if this theory is correct, then these other things will be true. So I'll give you one simple case of this matter, just difference between matter and antimatter. So one of the big things that any theory that tries to describe that has to explain or has to predict is how stable matter is. So just, your quick physics lesson here is, we're made of stuff. We're made of molecules. Those molecules are made of atoms, and inside those atoms is a nucleus made of protons and neutrons. And the only thing you need to know is that neutrons are a little bit heavier than protons, and so heavy things are also higher energy things. They tend to decay. So a neutron, given a little bit of time, will decay into a proton. But the proton is the lightest particle of its type. There's literally nothing for it to decay into. And so if you take a proton, you put it on a table, we have never seen a proton decay. As near as we can tell, they last forever.
Wow.
But they clearly can't last forever for exactly the reason we've already addressed. Because clearly at some very, 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 very tiny level, there has got to be a distinction between matter and antimatter, and that ultimately means that things like protons aren't stable. Mm-hmm. And so if you give it enough time, presumably a proton will decay into something. And so your theory is going to predict all sorts of things, but among much else, it's going to predict how long a proton should live. And so what we do is we get these giant, like, swimming pools full of stuff, basically, ultra clean water typically, and we look for a proton to decay.
Have we ever seen it?
We've never seen it. And so what we're able to do is every year that goes by and we're not able to see it, given the number of particles we're looking at, the sort of lower limit on the lifetime of the proton becomes a little bit longer. And I forget the exact number, but the minimum lifetime of a proton is something like 10 to the 36 years at this point. One with 36. By the way, that's a really good thing that the proton doesn't have a short lifetime, right? Because if it had a short lifetime, everything made of protons, like you and me, we would be annihilated pretty quickly. We would.
But 10 to the 36 for the listeners is one with 36 zeros.
Yes.
Okay.
Just a crazy. It's pointless to even because there's nothing else to compare that to, right? It's not like 10 to the 36 years. That's that's the lifetime of a sea turtle. I mean, It's many, 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 many orders of magnitude longer than the actual age of the universe. So some very, very small fraction of protons will have decayed so far. Even if that was the actual lifetime. But the point is that various theories that would have described how we had a symmetry in the early universe that sort of broke and gave us excess of matter over antimatter, some of them have already been ruled out. So we are able to make some predictions here, and the thing that distinguishes this from a religion, this is sort of circling back to your original question. One of the things that distinguishes theories like this from a religion is we're sort of forced to come up with an experiment that might disprove what it is that we believe. So, somebody has some idea, they've got some theory, they're like, there's going to be these particles, and there's going to be this reaction, and so on. And they say, and if that's the case, then a proton should decay in 10 to the 34 years. I'm thinking a smaller number.
Right.
And then we
it's
do
called
the
physics.
experiment.
It's called physics differences. Keep going.
So the point is that amount of they run the experiment and say, oh wait, no, that's the proton lasts longer than that. Clearly, this is wrong. And so I mean the level of proof is sort of indirect in a lot of cases, but it is very important that we don't just say, this is just this amazing idea.
Well, this is what as you speak, and as the people say, well, all right, man, they're trying to figure out whether a proton decays or not. What I find fascinating is that these questions exist in the first place, and that's what gives them their validity. So that you're a human being, whatever that means, and you're talking to these other human beings about these problems that on an everyday basis don't necessarily reflect our everyday reality. But here's what I find fascinating, what I find so valuable about this. There are a lot of people that sat in a room, mathematicians, came up with a very abstract theory and it took them a lifetime, or I don't know, 20 years, and they said, here's this theory. It bears no real, I guess, relevance to everyday life. However, 100 years later, some guy is trying to measure the inside of a conch shell or something, or whatever it is, and in fact, that mathematical theory actually does bear some relevance to the physical world, that's what I find so encouraging and so fascinating about this is that
it's not even just the connection between the pure mathematics and the physical world. It's oftentimes, I mean, I don't like to sell physics on the money making ability, but let me give you a sort of interesting historical example. So you had this guy Michael Faraday. There's a thing called Faraday's law. He was one of the most important people in the development of electromagnetism. And I don't need to tell you that electromagnetism, it is our world, basically.
Yes.
Everything we have now works on electricity and magnetism. We're obviously talking over and distributing this podcast over electromechanical devices. I mean, without electromagnetism, you just don't have any of that.
Right.
But early on, it was seen as sort of just a physics. It was seen as just intellectual experimentation. Why are you bothering with it?
An abstract thing, I guess, right?
And Faraday was talking to, I think it was like the Lord of the Exchequer, and he says to him, why is this interesting to you? Why are you bothering to do this? And he said, one day, sir, you may tax it.
Wow.
Which of course is true, right? I mean,
yes.
It was just a roundabout way of saying you don't know where all of it's ultimately going to lead.
But in a certain way, we do know, because at this point, like, we've seen, abstract physical theories turn into practical technological inventions, with the steam age, with the internal combustion engine, with electromagnetism, and now people are working on quantum computers and all of that sort of stuff. Like, without fail, all of those physical insights lead to engineering, which leads to technology.
Well, that's what I mean.
Sure.
That's what I mean by this conversation. That's what I appreciate about it, and the work that people like you do. It may seem abstract now, but it does. Whether or not your research or whoever's research, it builds on itself. And I guess that's what I'm saying, which is
right.
It's part of the march toward getting deeper and better understanding of who we are and where we come from and what we're doing here.
Well, but that's the other side of it, right? So there's the pure technology side of it, that adds to our quality of life, or may end up producing medical technologies or just fun devices that we can play games on. But the other side of it is, is a very real sense in which we do and have always wanted to know where it is we come from, where it is we're going, how we fit into the universe. And yeah, that may or may not be technology, but we want to have real answers to that, and those are the oldest questions. And we are sort of getting to the point where I'm not going to say, all of the ancients were dummies, and now we're finally getting to the point where we're answering them. No, it's a continuous process, and we're getting sort of more and more and more detailed answers, deeper and deeper answers. And one of the things that, one of the reasons that, again, I wrote this book is I think part of the forest gets lost for the trees, or vice versa. I can never remember how the expression goes. That we are basically, when we teach physics, when we teach even cosmology, we sort of teach the equations. But the reality is that all of what we understand, how we understand it, is that no, in fact, the overall laws are really, really simple. To calculate things, we need to do these equations, and we need to work out a bunch of complicated integrals or whatever. But the ideas themselves end up being fairly simple. And let me give you one sort of example, referring back to something we talked about earlier. I mentioned that one of the big symmetries in the universe is the laws of physics are the same everywhere. The universe doesn't care where you are, is another way of saying it. And I pointed out that there was no center to the universe. Well, so in the early 20th century, there was this wonderful mathematician by the name of Emmy Noether, who's sort of the hero of my book. And she showed something very, very important. She showed that for every symmetry that you have in the laws of physics, you can come up with what's known as a conservation law. And conservation laws are ridiculously important. They basically are laws that say whatever you start with, that's what you end with. And a very common one is, for example, electric charge. Electric charge is always conserved. So if you start off with a positive charge, you'll end up with a positive charge. Or if something's neutral, the universe itself seems to be electrically neutral overall, and it will remain neutral for all time. And most of these things that are conservation laws, and you may recognize a couple of them going forward, most of them were seen to be sort of fundamental. Like, they didn't come from anywhere. They were just an assumption about how things were. So, a very famous statement of conservation law is objects in motion stay in motion, objects in rest stay at rest, which is one of the ways of describing what's called Newton's first law of motion. And Newton, it was a law. That is what it is. But what's so amazing, and Newton obviously was no slouch, but what was amazing about Noether's contribution is Noether showed that the fact that the laws, her theorem, her famous theorem, showed that just by assuming that the laws of physics were the same everywhere, you could derive Newton's laws of motion. You could derive conservation of momentum, which is what his first law was, from first principles. It just comes from the fact that the universe is the same everywhere. What's known as the first law of thermodynamics is conservation of energy, and Noether showed that was just a consequence of the laws of physics not changing over time. It turns out just by making assumptions about symmetries, all of these things that you spend a lot of time in your college or high school physics class learning all of these equations about actually just drop out. They drop out naturally as a thing that our universe must do. And things that we thought, must be fundamental, it's like, no, actually.
So as you study the universe, these equations are actualized anyway.
Right.
Okay, so it's one. So you can start with the equation, or you can just start by studying the universe. You arrive at the same mathematical conclusion, essentially. Right,
but it's a bit like saying 1 + 1 = 2. Like if you're working with a little kid and you say to them, okay, I have a nickel and you have a nickel.
Right.
How many nickels do we have? And they realize you have 2 nickels, and then you have 1 apple and 1 apple, and you realize that adds up to 2 apples. And so you can do it on a case-by-case basis and realize, you can start to recognize a pattern. It is always the case that whenever I have 1 of something and you have 1 of something, there are 2 of them overall.
But Dave, we talk this way as laymen. The idea of symmetry. Let me give you some examples that I think is very interesting. Human beings seem to have a nostalgia for this notion of symmetry. As you were speaking, I started thinking to myself, we say things like this: "What comes around goes around. You get back what you put in." The universe rewards hustle, and I think human beings have this idea, and many times it's true that if you enter a certain contract in life, I'm going to be very ethical, I'm going to work very hard, I'm going to do what doesn't feel good in the short term because in the long term I'll be rewarded. Most cultures, certainly the philosophies and religions that we study, would bear that, would support the ideas that, being a good person, and we all know what that means, not snatching the baby from a woman's arms and selling it on the black market or something. These certain things that those are outside the bounds of natural law, the natural order of things. They would break the symmetry. They would lead to entropy, which would be a bad idea. So whether or not that's a reflection of the work you do is a different story, but I do think we, as human beings, seem to have nostalgia for some notion of symmetry, even when you start speaking in terms of ethics and morals and philosophy.
Yeah, I think there's a relationship certainly between what we're calling symmetry and what we might call order. Right?
Right.
So. And clearly, they're related in certain ways. You have, one of the most perfectly symmetric geometric figures, the circle. And it's very, very ordered, and it's very, very elegant. We like, again, symmetric buildings because they also seem very neat, very ordered, or a checkerboard or something like that. Again, the pattern is very pleasing. And again, there's a reason it shows up in not just art and architecture, but literature and all the rest of it. So, it does bring an important question, right? So it is both a fact of the universe that the universe has symmetries in the physical laws, very important ones, and we enjoy them. But then on the other side, we know we know, to bring up your ethical example, we know that disorder, we know that immorality exists, we know that, likewise, disorder exists. And the question is, how do you start with a universe that is, sort of perfectly symmetric and perfectly ordered, and end up with one that has such complicated structure, right? I mean, most of space is totally empty, but here we are living on this planet that's many, many, many orders of magnitude denser than the typical part of the universe, with very complicated life forms walking around talking on telephones.
Yeah.
Right? I mean, that is a result of clearly, very complicated processes at play. And one of the things, we live in this very interesting universe where sort of the rules are set up symmetrically, but there's an extra added component put into it, which is randomness, which, by the way, also tends to sort of figure heavily in, if not randomness, certainly capriciousness, perhaps, in a lot of myths. We have a really important built-in random component of the universe in the form of what's known as quantum mechanics. So quantum mechanics is one of the other great intellectual triumphs of the early 20th century, and it basically says, among much else, I'm going to simplify, it basically says that, if you see a ball flying through the air, we tend to look at it and be like, that ball is in a definite place, it's doing a definite thing. But in fact, it's not certain. There's a sort of fuzziness to reality. And by observing anything, you're basically there's basically sort of a random element to what you observe. And this shows up in a lot of different aspects of life. It shows up in radioactive decay. It shows up in all sorts of experiments. And it is the basis of solid-state technology, which basically is how microchips work. They wouldn't work otherwise.
I don't understand. In other words, I know the observer has its own sort of prejudice. The lens through which I view something does not necessarily make it a reality. It is my perception of it, but there's a very different reality going on in the grand scheme of things.
Right, that any observer... So, the famous thought experiment. So the famous thought experiment is this thing called Schrodinger's cat, right? And the experiment that Erwin Schrodinger, he never performed this, obviously, and he actually only came up with this idea just to sort of make fun of how quantum mechanics was thought of by the philosophers of science. But he basically says, imagine you take this box, and you have, sort of the classic quantum mechanical system, which is radioactive decay. So radioactive, if you have a radioactive source, basically it produces a little decay, a little photon, on average after a certain amount of time, maybe a second or 2 seconds or whatever it might be. But that's on average. Sometimes it can be longer, sometimes it can be shorter, and the whole randomness is, that's part of quantum mechanics. So, but imagine you shut a cat up in a box. And if the source decays in a certain amount of time, a vial will be broken and poison will be released and the cat will die. And if the thing doesn't decay in that time, then the cat will be fine. And the issue is, the question one that you just brought up is, does it matter if you look at it? Now, the way we normally describe quantum mechanics is, it really matters if you're looking at it, because it's by looking at it that you change it, which is the thing that ends up being so confusing.
Yeah.
And so the way you'd say it is, but if I don't look inside the box, did the thing decay or did it not decay?
If a tree falls in the woods...
That's right. But, the standard answer would be, before quantum mechanics, the standard answer would have been, the cat's either dead or alive.
Right.
You don't know, but you don't know a lot of things. So that's not such a big deal. But after quantum mechanics, for this particular sort of case, the issue would be, the cat is some combination of dead or alive, and it's by looking at it that you're forcing the cat to be in one of those states. You open the box, the moment you peek open the box, you are what are called collapsing the wave function. That's a fancy phrase. Collapsing the wave function.
So explain how that reality affects our how do we benefit from that in any way? Is that in our technology? I think you alluded to that.
Yeah, no, it absolutely does. Because a lot of so quantum mechanics shows up in just about everything we do. So, for example, a lot of the technology we use is based on the idea that electrons will be able to, I'm trying to think of the easiest way to say this, electrons will be able to sort of randomly tunnel through different materials. Right. And materials they shouldn't have been able to, they should either have been able to get through or not get through classically. But now they can sort of, just like an atom decays with some sort of random probability, they're able to sort of get through with some sort of probability. Right, and there's just tons and tons of technology that is ultimately built on that sort of picture, where, it produces, we're able to produce all sorts of diodes and things like that, and ultimately produces the microchip, ultimately produces computers, ultimately produces all of these other, all of this technology we use every day. Just about everything running on your desk is based fundamentally on these sorts of principles. As you alluded earlier, though, I mean, there's even other technology that we're working on now that's based even more directly on quantum principles, things like quantum computing.
Right.
Which, for your listeners, I mean, one of the cool possibilities, because there's these random components, since in some sense a quantum computer is in many different possible configurations at once, what it can do is it's supposed to be able to break encrypted data. So you've got your encrypted data, the quantum computer can be put on the task, and a code that would have taken thousands of years to break with a conventional computer can be broken virtually instantaneously with a quantum computer.
Man, oh man, say goodbye to privacy.
Dave, at least in principle, right?
Dave Goldberg, we're going to wrap this up soon. I don't want to take too much of your time, but let me ask you this: in a final question, do you see time travel as a reality eventually?
I think before I started thinking a lot more deeply about these things, I probably was a lot more. I saw it as impractical but possible,
right?
Because there's a huge amount of energies involved. The more I look into it, the more I play around with various models. It just seems like every single model that people come up with, and people do, serious scientists do, just so you know, come up with these things. They're almost always based on some sort of state of matter or something like that we've never actually observed to exist.
Right.
And so that gets to be a little bit suspicious. Like, if we could do this thing called exotic matter, then we might be able to make these wormholes and ... but it doesn't seem like that can exist or does exist. So unfortunately, I'm going to have to say, I'm pretty skeptical that it's even physically
What a
possible.
killjoy! What a killjoy!
Yeah.
I'm sorry. Can we take a second take? Yes, absolutely.
Dave Goldberg, man, you're an important guy, and I love that you're thinking about these things and making them accessible to people like us, and we really
And the
appreciate
book is a great read.
Yeah.
I mean, that's the thing. I need to read it and reread it and reread it and reread it.
No, it's great. The universe in the Rearview Mirror: How Hidden Symmetries Shape Reality. Read it and get closer to the truth, ladies and gentlemen.
Yeah.
And it is not a guide for time travel. Whatever, Dave Goldberg.
Whatever.
Professor.
Because let me tell you,
PhD. Dr. Dave Goldberg out of Drexel University.
Thank you so much for having me.
Thank you.
Thank you, man. You're awesome. Thank you so much.
And just for the record, we may not know whether exotic matter exists, but we do know that DeLoreans exist. So time travel is possible.
Yeah. The Back to the Future reference. Go teach. Go spread wisdom.
I'll
Professor.
do my best. Thank you so much.
And write more books.
Ooh, that's right. Later.
Bye-bye.
Bye.
All right, ladies and gentlemen, another mind-blowing episode of the Brian Callen Experience. Bye-bye.
You've been listening to The Brian Callen Show with Brian Callen. Be sure to like him on Facebook. Just search for Brian Callen Comedy. And follow him on Twitter. Just search for @Brian Callen. You can also find him online by visiting his website. Just go to briancallen.com. Until next time, bye-bye.